to try this in PowerPoint. And mostly, again, we're using PowerPoint full slideshow mostly for the tools that allows you to just use your mouse to kind of grab and draw. Though it's a little, like I said, unsteady with my mouse here, we'll still give this a try. I'm going to go a slideshow from the beginning, and I've got just a blank slide here. So in Microsoft, a great thing about full screen show is you can use the pointer options and draw. And I'll just try a ballpoint pen here. And what we wanted to go through here is what we did last semester. I've mentioned it once before, weighted average or centroid calculation. So let's see if we can do a little bit better. Centroid. Again, my inspiration for this format is Sal. He is my local hero. Just dying to know why he's out there in California doing what he's doing, but loving it. And I hope you all do too. Let yourself explore with some of the other stuff that he does out there. Perhaps the Geithner plan might be something to do. But the centroid calculations is exactly what we're doing when we're calculating a resultant. And so if one of the problems you'll see very often might be a pool that looks something like this, where you might want to know what is the center of pressure on this face there. Now if you draw that face off to the right side, you can think that that is a straight line. This point having some pressure equaling to gamma depth right there, and this point here having some pressure equaling gamma depth right here. I'm not drawing these to scale, but we'll try to do that a little bit later. This might be 3 gamma, this might be 8 gamma, and what you then have, sorry, that should be a trapezoid, which can be divided into a triangle and a rectangle. And all essentially you are doing is you are calculating the weighted average of the centroid of this and the centroid of that as projected down to that pressure surface. So it's a weighted average. The key to any of these problems for centroid calculations, and you're going to see eventually it's important to know where the centroid is in the x, y, and the z. But in our case, you can kind of just turn this thing right here, that line, I'll give it an A to a B. And you can pick some logical point. I'm going to pick the bottom right here, and I'm going to draw A and B here. And I'm going to then kind of draw that straight line, see what I can do. Not so good, not so bad. And then 8 gamma here and 3 gamma here. Probably about right. And realizing we could use mass prop and get the area, but come on, we don't need to do all that all the time. It's just our nice kind of fallback. It's much more efficient to do this. Break this up into a triangle and a rectangle. Establish my datum right here. My origin is going to be right there. And very often you'll see eventually I will sometimes tell you to pick an origin even farther away, just in case you're going to be doing adding something to this. So you could even have picked an origin right here, but for now we'll pick an origin there. We then sketch out with our finger what is the centroid of that one and what is the centroid of this one. And you want to put it in the 3D centroid or the 2D centroid. In other words, this is the middle of the rectangle, this is a third from each end on the triangle. And then you do the calculation here. The sum of the distance to the centroid times the area for each of those little pieces. So distance to the centroid, so from n equals 1 to n. And this is the number of pieces you have. So this would be the first piece, this would be the second piece. You take that entire thing divided by the sum of the areas. And if you remember, the area under this thing had units of square feet times pounds per square feet or pounds. So the area is actually in pounds, and this is actually in foot pounds. Foot pounds divided by feet is feet, and that will get you the weighted average of the centroid. So more or less you've got something acting with pressure down towards that face, perpendicular to that face, and another something acting with pressure, got to get myself a straight edge. All right, you've got this area times this distance plus this area times this distance divided by the sum of the areas, and that will get you the distance to the centroid. Now you can do that in the x, and you can do that in the y, and eventually you can do that in the z, and you can actually get the 3D centroid. So that's how you go about doing a problem for a resultant, determining where the resultant is. The way the book goes about doing it is a good way for transferability to more significant problems, but you should first and foremost be able to just look at any face, say that the pressure is acting perpendicular to that face, draw in your shape, and then do the calculation. So let's see if we can go to a new page here. Will it let me do new page? It won't. Alright, so we'll go back, and I'm going to just go ahead and save this. I'll work on the corner here. Let's give you one more example of this. Let's say I had a circle and a square, and they were sitting along a board that began right here. Now what would be the, let's say the circle had a radius of r, which would mean from here to here, and the square had a side of 2r. Right? Where is the centroid of this? Well, first you'd realize it's more in the square than it is in the circle, right? Because these, if this is from here to here is r, 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 this is 4r. Right? 4 times r. And you'd have to look at it and go, by golly, it's a little bit over to the right here, and that's the first thing you're going to be doing with a centroid calculation. But now, instead of that, you can do this calculation, which is the sum of the distance to the centroid times the area divided by the sum of the areas. Well, the areas are equal to pi r squared times 4r squared, right? And you're going to see this in estimating pretty quick, this comparison of a rectangle and a circle. So that's my area. So we're going to add those up, and we get what? 4 plus pi, 4 plus pi, right, taking that out, times r squared. Got to get that bamboo so I can actually write it. Okay, so that's the area. What would be the distance to each one? Well, the first one would be the area pi r squared times r, and the second one would be 4r squared times 3r. So the numerator would be pi r squared times r, or pi r cubed. That would be this area times this distance plus, right, 4r squared times 3r, or essentially what would be 4 times 3r cubed, right? This comes from the fact you're going to take the area of 4r squared and multiply it by the distance from this origin there of 3r, and so you get 12r cubed. What you get here now is 4 plus pi, 12 plus pi r cubed divided by the area 4 plus pi r squared, and that's where your centroid ends up. So I'm going to post this one out, and we'll see how to do this better. Boy, got to work on. I ordered a bamboo about 8 weeks ago, and it never came through. Bamboo is got a pen interface. We'll do this on the board today. But understand that's how you do centroid calculations. I sat down with a couple of students. The rest of it in hydrostatic problems and many other problems is just then to apply the concepts of moments and free body diagrams. So the centroid calculation, the mathematics, I will show you the integral mathematics. Finally, integral mathematics is the integral of x, or the distance, times dA, right, evaluated over the entire area, over A. Because what you're doing is you're taking this and breaking it up into little tiny pieces. So that's the actual centroid calculation. You'll see that come at you in a number of different ways, and it could be X or Y or Z. But what we do is we take the sum of the distance to the centroids from some established origin or datum times the areas and divide it by the areas. That gets us to the distance of the centroid. You remember the area. If a pressure distribution, area versus pressure gets us force, just like weight times distance. I'm sorry. Just like unit weight times volume gets us force. All right, we'll see if we can end this. Exit. Click. And finish our screen capture.